Okay, NRD 10. Okay, so we've got some formulas here for centroid. And by the way, I'm not going to justify these. I claim that these are pat standard physics facts, and there's good reasons why they're true, but you can just take those as just given. But intuitively, I mean, this is the center of mass idea that you're kind of accustomed to. In other words, does that make sense? Do you have a good intuition for center of mass, or what that sort of means?
Yeah.
Yeah. Okay. Yeah. So, for example, if I wanted to talk about the center of mass of this book, right? What that means is that there is some point somewhere on the book that if I put my finger under that point, the book would balance, right? If you put it somewhere else, it's going to fall over. Yeah. Okay, so given these formulas, the specific problem is to compute the centroid of this particular region, and here's the region. We'll see x squared plus. So it's part of this disk of radius r. But specifically, it's just the part where x is greater than or equal to 0. So it's just this here. And that didn't really show up very well, did it? It's just that. Cool? Okay. So by the way, geometric, or let's say physical intuition, you could probably guess it's going to be somewhere on the x-axis. So we're probably expecting y bar to end up being equal to 0. Okay. All right. But you still do have to compute that. So let's do the more interesting part is to compute x bar. Let's do that first. And we have a formula. So this is our domain. Let's call this set D. So we're looking for an integral over D. Well, excuse me, wait a second. The first thing we've got to do is compute the mass, because the mass is part of the formula, and the mass itself is an integral. The mass is that double integral, right? And conveniently, this density is constant. It's just 1 in the statement of the problem, so that density just factors out as, well, it's just 1 times double integral of 1 dA. This, of course, is just the area of our domain D. And the area of the domain D, that's an easy, this is a disk of radius r. Well, it's a half disk of radius r, that is. And so this is 1/2 pi r squared. So I claim that that's the mass. Does that make sense? Okay. Okay, so when we look at our formula for x bar then, x bar is 1 over the mass times this double integral x delta dA. And so I can rewrite the mass right off the bat that this is 2 over pi r squared and then double integral x. Density is 1 still, so I'm not even going to write that down, and then dA. Okay. All right, so now we just need to compute this integral, and I can turn this double integral into a nested integral in 2 different ways. I happen to recall that either way you slice it, as the saying goes, it's going to work out sort of okay. But it's different depending on which way you slice it. So I'm going to just arbitrarily choose one way to do it, and you can try to do it the other way, and it's about equivalent either way you do it. So let me rewrite this as double integral x dx dy. That's too bright. Okay, there we go. Okay, so what's the range of values for y? Again, you got to do your outside bounds first when you're slicing. So if you're doing your y slicing, well, y goes from -r to r. And now for a given value of y, there's an x1 and an x2. Right? And x1 is clearly 0. And what is x2? Well, and that point, that's on the circle. The circle has the equation x squared plus y squared equals r squared. Solve for x, and you get square root of r squared minus x squared. Square square root of r squared minus y squared. Sorry about that. Cool. Okay. All right. So now it looks a little ugly because you've got a square root in the bound, but good news, when you do the x antiderivative of x, you get an x squared, so the square is going to make the square root disappear. So this works out sort of okay. You get 2 over pi r squared, integral negative r to r, 1/2 x squared. X goes from 0 to square root of r squared minus y squared. And that, not so bad. Plug in 0, you get 0. Plug in this square root, that kills the square, and altogether you get just 1/2 r squared minus y squared. And you can kill the 2's, and now you just have a single variable integral. Does that make sense?
Yeah.
Yeah. So just for fun, by the way, I mean, just for kind of the practice of seeing how it works out, I'm going to recommend that everybody try doing this the other way. Try doing it with the dy on the inside and dx on the outside. It ends up being a different integral, but it's still doable. Yeah.
And then you do the same for bar y, then it becomes 0.
To find y bar, it's just that that's going to be a y. There, that's going to be a y. Yeah, that's right. Same bounds now. All the bounds are the same because it's still the same domain, right? But yeah, just be a y instead of an x, and so again, that changes the way the integral works out. Yeah.
Thank you.
Yeah, no worries. Does that make sense to everybody? And side note, by the way, it does turn out that y bar is equal to 0, and so your centroid ends up being about like that.
Remind me again, what does x bar stand for?
So x bar that's the x coordinate of the centroid. So your centroid is a point. That's the point of support where you put your finger and it balances, right? So x bar is the x coordinate of that centroid point. Oh. Okay. All righty. Let me stop the recording here.